Welcome back to the workshop. We're going to continue taking a look at integration or anti-differentiation. And in Calculus 1, we're relatively limited on integration techniques. It's actually here in Calculus 2 where we will develop more integration techniques. Things that you should be familiar with Calc 1 are essentially substitution and integrating polynomials and a few special trigonometric cases. So what should we be familiar with? Well, again, we have a nice formula sheet that's going to help us out quite a bit. Again, that will be available. So let's take a look at the formula sheet really quickly. So here's our notes, but here's the formula sheet that I will be happy to share with you guys. Things that you should be familiar with from Calc 1 essentially bring you all the way up to 17 here. So 18, 19, 20 will actually add in here in Calc 2 in our next chapter. So these are the basic integration formulas. We'll actually see the idea of integrating using tables where we have hundreds of formulas for integration, which really aren't, I don't know, they're good to use, but we'll talk about that later. All right, let's see here. So constant multiple, sum and difference, derivative of 1, or sorry, the integral of 1 is just u. Let's see here, power rule. Actually, this guy we learn, and this guy we learn in our next chapter as well. So we're maybe not familiar with those yet. As well as this one. Oops, this one. All right, so there's a few that we will be taking a look at in the next chapter, but many of these we should already be familiar with. In particular, these first 4, along with the trigonometric ones. These trigonometric ones. Oh, actually, no. Sorry. This one, this one, this one, and this one we'll learn in the next chapter as well. So it's kind of a hodgepodge in terms of which ones you should be familiar with and which ones you're not. The nice thing is that at the end of our next chapter, you're familiar with them all, or you should be. So that'll simplify things a little bit. But what can we do? Well, essentially, we have a few basic integral rules that we just looked at, but we also have the method of substitution. And so we just want to do a couple of examples here where we have a substitution. So let's see, the integral of cosine x times sine cubed of x dx. And this is a little bit weird. You're like, oh man, there's no rule for that. I don't know. But we do have a rule for sine and cosine, and those are relatively straightforward. And one important thing is that we know that the derivative of sine is cosine. So in this case, right, I don't have a rule that I could just apply immediately. So I want to try a substitution. So I want to let u be equal to, let's see here, I have sine being cubed times cosine. So I'm going to take sine here and let u be sine of x. And why do I do that? Well, this is the most complicated thing, and I'm going to try to simplify it a little bit. Essentially, you can think of it that way. Also a little bit of foresight and a little bit of knowing what's going on, not because I have seen the answer, but because I have enough practice, right? So what do we need to do in order to be able to see these things? Practice. So I would encourage you maybe to take a look at your text, go back to the chapter on substitution, all right, log into WebAssign, open the e-text, go to the chapter on substitution, and take a look at some of the examples from the text and take a look at some of the problems if you need some additional practice. So if we let u be sine of x, then finding the differential, right? Finding the differential du would be, take the derivative of sine x, which is cosine x, times dx, right? The differential is equal to the derivative times the differential. And this gives us our complete substitution. And that looks very good because I can regroup these things, right? This is sine of x being cubed times cosine of x dx. Now I can see that what I have is u cubed times du. Easy enough. Now I have something that I can, it might be easiest to manipulate it. I can recognize that if I were to have the integral of 4u cubed du, then I would have just used the power rule to get this. Okay, but I don't have the 4. So by introducing it, I also need to introduce a 1/4 because 1/4 times 4 is 1. So I've effectively done nothing. So this is 1/4 times u to the 4th plus c, but I need to substitute back. So this is 1/4 sine to the 4th of x plus c, and that's it. So that's our method of substitution. Does our substitution always look quite that simple? Is it, oh, hey, you do the substitution and you can observe that what we have is essentially the power rule, or essentially just the chain rule, or essentially just one of these basic rules? Not necessarily. It could look a little bit more complicated than that. So this one is an example of that. So using a substitution, again, what we want to do is we want to simplify the most complicated thing. So is x squared complicated, or is the square root of 1 minus x complicated? Well, I would argue that the square root of 1 minus x is complicated. But much like I didn't replace sine cubed of x with u, I'm not going to replace the square root of 1 minus x with u. I'm just going to let u be equal to 1 minus x. Because I'm going to try something. And in fact, I don't remember how this turns out. So this really is genuinely me just trying something. So once I do that, then I have du is equal to negative dx. That's not terribly complicated. It seems like it's hardly worth doing. But one thing that we want to recognize is that we have an x squared here. So I'm also going to have to take this thing. So if I take my u is equal to 1 minus x, and I want to find what x squared is, then what I'm going to do is I'm going to subtract 1 to get u minus 1 is equal to negative x, multiply by a negative 1 to get 1 minus u is equal to x. Okay, when I multiply by a negative 1, I get negative u plus 1, but I like to write that this way. And then square both sides to get 1 minus u squared is equal to x squared. So when we make our substitutions now, we have to do a couple things first. We might want to recognize that we have, let's see here, x squared, that's not a problem. Square root of 1 minus x, that's not a problem. But we don't have a negative dx. What we have is just a dx. So I want to add a negative to that. But when I add the negative, I have to get rid of it as well, and get rid of it there. So negative times a negative is positive, giving me what we started with. There are other ways that you can approach this substitution, and that's absolutely fine. Some people would say, multiply it here. So negative du is equal to dx. And now you just replace the dx with negative du, which is where that negative appears. So it doesn't matter. It's fine. No worries, as long as the steps you're doing are not wrong. There's just multiple options for right steps. All right, so now that I have this, I can make my substitutions. So this is the negative of the integral. X squared is 1 minus u squared, and then this is the square root of u du. Does this look better? It's hard to say yes, but in reality it does, because what I can do is I can expand this square to be 1 minus 2u plus u squared times the square root of u du. Now, why is that better? Because I can distribute the square root of u in to end up with, I'm going to write this really nicely as u to the 1/2, right? Square root is exponent 1/2. Distribute it to the 1 minus 2 times u to the 1 plus 1/2 is 3/2, plus 2 plus 1 is, let's see here, 5/2, u to the 5/2 du. And now this looks really nice because I just need to apply the power rule a bunch of times. So this is going to give me the negative of, all right, so u to the 1/2, I'm going to increase the power by 1. So that's going to be 3/2. but the coefficient needs to change a little bit. So I increase the power by 1 and I multiply by the reciprocal 2/3. So that way, when I take the derivative, 3/2 times 2/3 gives us back the 1. And now I have 2 times. I'm going to include a new coefficient here, new factor, increase the power by 1, 5/2. I need to multiply by the reciprocal 2/5 plus u to the 5/2, increase the power by 1, so 7/2, multiply by the reciprocal 2/7. And then I have my plus c at the end. And then I substitute back. We have u was 1 minus x. So this is negative 2/3. U was 1 minus x, 1 minus x to the 3/2 minus 2 times 2. Distribute here. So negative times a negative is a positive. 2 times 2 is 4, 4/5, 1 minus x to the 5/2. Negative times positive is a negative. 2/7 times 1 minus x to the 7/2 plus c. And I'm done. So this looked kind of tough to approach, but it's not that bad. We perform a substitution and it becomes essentially just a bunch of applications of the power rule and the constant multiple rule. All right, so we'll pause for now and take a look at definite integration as well, which is pretty straightforward, just looks at the fundamental theorem of calculus. So I will see you guys back in the workshop in just a moment.